Hey physics friends, Mr. Collier here. Today we're going to continue our discussion of dynamics, continue our discussion of joules as we change from talking about work to talking about the other side of that same concept, energy. So energy comes in a lot of different forms. In chemistry, you might have talked about chemical energy and thermal energy. You've possibly talked about solar energy and electrical energy. And of course, this is a course on mechanics, so we're going to be talking about mechanical energy. So energy is defined as the ability or capacity to do work. So as we've already mentioned, it's measured in the same units, joules, that work is measured in. And like work, it is a scalar quantity. We use positive and negative to indicate whether energy is being added or removed, but it's not directional the same way a vector is. As I mentioned, we're going to measure it in joules. There are other units for energy like calories, British thermal units, or foot-pounds, depending on how you want to communicate different things. But we're going to stick with the joule in this class. We're going to discuss two types of mechanical energy in this class, kinetic and potential. Kinetic comes from the Greek word kinetikos, which means motion. And that's what we're going to talk about first, the energy of motion, kinetic energy. This is a measure of the recoverable work done in changing the state of motion of an object. So let's unpack that a little. If something is at rest and starts moving, right, it must have had a net force. If something was in motion and it comes to rest, or any change in velocity requires a net force. A net force on a thing that's displacing it is going to do work. It's going to change its energy, and that is what kinetic energy is, a measure of how much that work is done, how much kinetic energy is in an object. The equation is written like so. We can write kinetic energy as Ke, or E with a subscript K, and it is equal to 1/2 mass times velocity squared. This squared velocity means that the speed of the object is a little bit more important than the mass of the object. So yeah, massive objects have more energy than objects that are smaller, but the velocity is really what determines the kinetic energy of an object. So real quick, m is for mass measured in kilograms, v is the velocity of the object measured in meters per second, and that will give us kinetic energy in joules. Another thing relevant to the kinetic energy of an object is the WorkEnergy Theorem. This simply says that the net work done on an object is equal to its change in kinetic energy. And you can write that as an equation. Net work is equal to the change in kinetic energy. Basically, if you make an object speed up or slow down, you've changed its kinetic energy, and you've also, therefore, applied a force and moved it some distance. So the net work will be equal to that kinetic energy. Now, you're not doing any net work when you lift an object against gravity, but we will talk a little bit about how that energy gets stored when we talk about potential. So as you head into homework 5-3, which will be all about kinetic energy, you want to remember some previous equations we've looked at. Work is equal to a force times a distance, a force is equal to mass times acceleration, and we can use kinematic equations to solve for acceleration. So all these terms are very closely related, and all of the units can work together, cancel out, and give you the units for joules that you need. The second piece of mechanical energy is potential energy. This is energy that is stored, and it comes from position or condition. Now, there are some other types that we won't be talking about, like chemical potential, but we're going to focus on two types here in just a minute. So this potential energy is stored energy that is a measure of the recoverable work done in changing the position of a body. So what does that recoverable work mean? It means that it's work that you do against gravity or against some force that can return that work, return that energy back to you. When you lift an object off the ground, it can give you that work back if you let it fall. Non-recoverable work is work done against friction. So when you're sliding something left or right in sort of the x-axis, that work done by friction does not get stored in a meaningful way that you could get it back. It kind of just turns into heat, goes into the surroundings, and you can't recover it. So we're going to be talking about two types of potential energy. The one we're going to spend more time on is gravitational potential energy. A lot of different ways you can indicate it. I think I will most often use potential energy like that, PE, but it's also a U in some textbooks. You can say GPE for gravitational potential, or just a capital E for energy with a little p. But the equation is the same for all of these. It's mass times gravity times height. Mass needs to be in kilograms, gravity in meters per second squared, or another way to think of gravity is newtons per kilogram. And the height is going to be measured in meters. The height, something important about that is it's relative to some arbitrary reference point. So you can say that this object is here, and so everything below it has negative potential energy, and everything above it has positive potential energy. But you could just as easily rearrange it and say, well, my reference point is now down at the bottom or up at the top. And so the reference point is key to whether your potential energy is positive or negative. So that'll be something to keep in mind, and you'll see that in your homework. And of course, potential energy will be measured in joules. The other type of potential energy that we'll take a brief look at is elastic potential energy. And we did already talk a little bit about springs. And work is energy and energy is work, so whatever work you do on a spring is how much energy is stored in the spring. So the equation for the elastic potential energy is actually the same as the spring equation for work that we already looked at this chapter, 1/2 K, which is the spring constant measured in newtons per meter, and x squared, which is the elongation or compression of the spring in meters, and that'll give you the elastic potential energy in joules. So with that information, you are ready to go tackle 5.3 and 5.4. Good luck.